because this is contained, in fact, in the equations of general relativity, and this was done a little bit later, in fact, by Friedmann. On the other hand, also in 1947, also Einstein wrote, since I introduced this term, I had always a bad conscience. I'm unable to believe that such an ugly thing should be realized in nature. Now today we know that the cosmological constant does exist. And also we have to face the following problem. Without the cosmological constant, the general theory of relativity is the most beautiful physical model ever proposed. With the cosmological constant, it is the worst theory ever proposed. Because it introduces a new constant and parameter whose physical meaning is totally unknown, and its numerical value cannot be predicted by the theory. So, without the cosmological constant, we have the most beautiful theory of physics. With it, we have one of the worst theories ever proposed. Now, I have mentioned, in fact, in the Friedmann equation, there is a parameter k. Now, this parameter describes the geometry of the universe. There are three possible geometries. So, if the density of the matter is greater than the so-called critical density, then the universe is a so-called closed universe. And it looks, its time evolution of its size looks like this. So this means that in fact this kind of universe may undergo an infinite series of oscillations. It starts with a big bang, it expands, then it will collapse, and this cycle can go almost forever. Now, if the density is equal to this value of the critical density, the universe is called flat. This is the flat universe, and it will expand forever. Now, if the density is smaller than this critical density, the universe is called open. And again, it will expand forever, but with a different speed. Now, in purely geometrical terms, the corresponding geometry for the closed universe and for the spherical space has the following property. The geometries can be described very easily in terms of the sum of the angles in a triangle. And in a spherical space, the sum of this angle is greater than 180 degrees, and somehow if we would be able to draw a triangle, it will look like this. So the spherical space of the triangle looks like this. And the sum of the angles is greater than 180 degrees. In a flat space, is the geometry we know, with the sum of the angles 180 degrees, and in the hyperbolic space, which is also called the open space, the triangle looks like this, and the sum of the angles is smaller than 180 degrees. So the behavior of a triangle from the sum of the angles gives us a geometrical understanding of the universe. Now, in fact, we know from observations that the geometry of the universe is exactly flat. So this is the case which is happening in the real universe, and this implies that that coefficient k is equal to 0. So this is again another representation of how these geometries may look like and how they can be somehow realized in nature. And I'm sorry I talk here so much, but I'm very close to them, because this is almost the last section, but the last, yes, about the so-called accelerating universe, which I have already told you that it was the last great discovery of the 20th century. And it was somehow accidental. Because by 1992 or 1993, some scientists from Berkeley, in fact there were three groups, at least now there is some debate who started this idea in Australia, in the United States, and so on. I have chosen this gentleman mainly because I like this picture. But there are in fact at least three gentlemen, and if I'm not wrong, they were awarded the Shaw Prize. Yes. It was Permuter, Brian Schmidt from Australia, and Aidan Rees. At least there are at least three groups. But because this gentleman has the idea of making this very nice photo, he is the most popular of all the scientists. And they tried in fact to use the supernovae to determine the cosmological parameters, because the value of determining the value of the Hubble constant is very, very important, and there are many other cosmological parameters. And a very good project is to use supernovae to determine these parameters. And in the standard approach to cosmology, it was expected that in fact the universe is decelerating. Why? Because the galaxies that are more far away, there are two forces acting on them. On the one hand is the force of the expansion, and on the other hand is the gravitational force of the matter behind the galaxies. And this gravitational attraction would make the galaxies to decelerate. So the rate of expansion of the universe should in fact should be lower and lower. The motion, the expansion should decelerate. This was the common understanding of the expansion of the universe up to 1999. When these three teams of scientists in fact reported that the universe is not decelerating. It is in fact accelerating. So instead of going slower and slower, the universe expands at a faster and faster rate. And this is the very important discovery of the accelerating universe, the fact that the universe is accelerating. Now, as I mentioned, this result is related to the study of the supernova. And a very famous supernova is in fact the supernova observed in July or August 1054 by some Chinese astronomers. And it was in the times, it seems to me, of this answer, or anyway, or in the same dynasty. And this supernova, which was recorded at that time, is called the Crab nebula. So you may understand what means a supernova explosion, because after 1,000 years from this explosion, in fact, the filaments of this nebula are expanding at the speed of 1,000 kilometers per second. Well, the supernova is a very big explosion, very powerful explosion. So, what are supernovae? They are exploding stars, and they represent the very final stages of evolution for some astrophysical objects. When this explosion takes place, a huge amount of energy is released. And the energy emitted is 10 to the power 20 times the energy produced by sun in 1 second. So in 1 second, the supernova explosion should emit 10 to the power 20 more energy than the sun. So they are very luminous, they are very big explosions. Now, supernovae have been classified according to their spectral characteristics. So first of all, there are supernovae that contain hydrogen, and they do not contain hydrogen, they are spectral. Those who contain hydrogen are called type 2 supernovae. Those who does not contain hydrogen are called type 1 supernovae. Now, type 1 supernovae are subclassified according to the presence of the element called silicon. And those who contain silicon are called